Okay, this is part 2 of energy calculations. And here we're going to look at standard enthalpies of formation. Now, this has a strict definition that we must follow. And here is the symbol for standard enthalpy of formation. It's delta F H naught. Okay, so the standard enthalpy of formation is the heat change for the formation of exactly 1 mole of a substance from its elements in their standard states. So let's take a look at the elements in their standard states. Metals. Their standard state is a solid, except for one metal, which is mercury. Mercury is a liquid. But every other metal, the standard state is a solid. Sodium, its standard state is a solid. Nonmetals. Well, it depends on the nonmetal. Some of the nonmetals are liquids, some are gases, and some are solids. So let's take a look at the nonmetals that are solid. First of all, carbon is a solid in its standard state. Phosphorus is a solid in its standard state. Sulfur is a solid in its standard state. Selenium is a solid in its standard state. Iodine is a solid in its standard state. Okay, now let's look at the liquids. Bromine is a liquid in its standard state. And notice I put Br2 because it's one of the Hunkelbriefs, one of the diatomics. What about the rest of them? They're gases. So that includes nitrogen, which is N2, O2, F2, Cl2, and then, of course, the noble gases, helium, neon, argon, krypton, xenon, radon. So their standard states are gases. So you should know the standard state of all of the elements now. It looks like that as far as liquids go, there's only 2 that have a standard state of being a liquid. And as far as gases go, there's only these right here, the noble gases, and these 4. So if you can memorize the standard states, the 2 liquids, mercury and bromine, and if you can memorize the standard states for the ones that are the gases, then you know the rest of the elements are solids. Okay, so here are some examples of standard enthalpy of formation reactions. So we want to form 1 mole of bromine liquid. What is the standard state of bromine? Well, it's made out of bromine. And what is the standard state of bromine? It's a liquid. So what is the enthalpy of formation to take 1 mole of bromine liquid and turn it into 1 mole of bromine liquid? And the answer is 0 heat, 0 calories, 0 joules. Now, what if you wanted to make 1 mole of bromine gas? Well, the standard state of bromine is Br2 liquid. So here, how much energy is the energy change, the heat change, going from bromine liquid to bromine gas? Well, here, this would actually release energy. I don't know why that says positive. It should be negative. This is an exothermic reaction and it would release, oh no, I'm sorry. It's an endothermic reaction because we're boiling the bromine. So it's 111.884 kilojoules per mole. And you can actually find these values in the back of the book. So let me show you the book so you can see these values. So this is in the appendix, and this is alphabetically by the way the element is spelled. So here's bromine, and you can see that for Br2 gas, the standard enthalpy of formation, liquid, a gas is 30.91. Oh, I wrote the wrong number down. Good thing I went and checked here so I can fix it. Plus 30.91 kilojoules per mole. And here, this is a standard enthalpy of formation reaction. So here we have H2O gas, And what are the elements that make it up? Hydrogen and oxygen. And the standard state of hydrogen is a gas. The standard state of oxygen is a gas. And oh, I need to add that to my list back here. Now that I think about it, H2 is a gas. And this is the standard enthalpy of formation reaction, and it's minus 241.8. And let me see if we can find that value. So standard enthalpy of formation, we're going to look for H2O. And let's see where that is. So here's hydrogen. And here we have H2O gas is minus 241.83. We have 241.8 written down, but that's okay. Now, let's do one more. Only this time, instead of being given the reaction, we're going to write it out. So this is how you do it. So let's find the standard enthalpy of formation of H2O liquid. So to write the reaction out, what you do is you look at the elements in the compound. The elements are hydrogen and oxygen. Next thing you do is you write down a 2 if they're a Henkelbrief, if they're one of the diatomic molecular elements. And these are both Henkelbriefs. So we put 2 here and we put 2 here. Next thing I like to do is I like to put down its state. H2 is a gas at room temp. Oxygen is a gas at room temp. And then I like to fix the coefficients. So here we have 2 hydrogens, and here we have 2 hydrogens. Here we have 2 oxygens, and here we have 1. Now, normally when we balance a reaction, we put a 2 here to get 2 oxygens. But because of the strict definition of an enthalpy of formation, which is the formation of 1 mole of product, we can't change the coefficient in front of H2O. So we have to change the coefficient in front of O2. And we put a 1/2. So that explains why we have a 1/2 here. It's because this coefficient has to be 1. Okay, and we look at the value for this, and we find out it's minus 285.8 kilojoules per mole. Okay, so that's how you write a standard enthalpy of formation reaction. Okay, here are some things that you want to know about standard enthalpies of formation. The standard enthalpy of formation of an element in its standard state is 0. So that means to take an element in its standard state and to turn it into its standard state takes no energy. Most enthalpies of formation are negative, which means they're exothermic. And these values can actually be compared for stability. The more exothermic it is, the more stable it is for related compounds. Okay, so let's take a look at some problems here that we're going to solve. So the first problem is for standard enthalpy of formation. Write a balanced chemical equation for the formation of CH3OH liquid from the elements in their standard states. So we're going to write down CH3OH liquid. And the next step is to identify the elements. There's carbon, hydrogen, and oxygen. So I'm going to put carbon, hydrogen, and oxygen. You can see I'm spreading that out. Now I want to fill in the Henkelbriefs. Which ones come as pairs? Hydrogen comes as a pair, oxygen comes in as a pair. Now I want to identify which ones are liquids. Well, none of them are because there's only 2. Bromine, and mercury. Now I want to identify the gases because that's a smaller subset also. Hydrogen is a gas at room temp, and so is oxygen. So that means that carbon is a solid. Now, the next thing I want to do is I want to put the coefficients in. So here we have 1 carbon, and here we have 1 carbon. That's great. We're done. Here we have 1, 2, 3, 4 hydrogens, and here we have 2. So I'm going to put a 2 in here for the hydrogens, and I'm going to go ahead and put that plus sign there. And then we're going to look here and we see we have 1 oxygen and we have 2 oxygens. Remember, we cannot change this coefficient, so we have to change this one. So how do I get 1 oxygen when they come in pairs? I put a 1/2 here. So you're going to see a lot of coefficients in these standard enthalpy of formation reactions where you have a fraction here. And that's the common thing to do, is to put a fraction there, not to put a decimal, not to put 0.5, but to put 1/2. So here's the standard enthalpy of formation. And to look up the value, we go to our index or our appendix. And here we go. Here's the appendix. And these are not the values. Got to go a little, oh, I went too far. So here I can see the standard enthalpy of formation. Now we're looking for CH, so I'm going to look for compounds with carbon in it. So here we have some compounds with carbon in it. And here you can see I have CH3OH. Let me move the book a little bit. And here that's a gas. And according to us, we want it for a liquid. So here we go. CH3OH liquid. It's minus 238.4 kilojoules per mole. Minus 238.4 kilojoules per mole. And I'm going to double check that number. And indeed, that's what it says. So that's how you answer a question like this. Okay, let's take a look at another one here. Write a balanced equation for the formation of 1 mole of Cr2O3 from chromium and O2 in their standard states. Find the values for, and this is called chromium 3 oxide in the appendix. So hit pause, write the equation out. After you've written the equation out and figured out the enthalpy of formation, then hit play and see what I do. Okay, so now you've hit play again. Clearly you finished. So I'm going to put Cr2O3 solid here. I always start with the product, exactly 1 mole. And the elements are chromium and oxygen. And which of these are doubles, Hunkelbriefs? Oxygen is one of them. And that's a gas at room temp. Chromium is a solid at room temp. So here we have 2 chromiums, 1 chromium. So I'm going to put a 2 here. Here we have 3 oxygens. Here we have 2. So I'm going to put 3/2 here because 3/2 times 2 is 3. So here's the enthalpy of formation reaction. I'm going to look up chromium in the back of the book. And remember, these are alphabetical. And the back of the book has that the enthalpy of formation for this is negative 134.7 kilojoules per mole, and that's mole of reaction, of course. So there's your standard enthalpy of formation for this reaction. Okay, now lastly, we have using standard enthalpies of formation in the appendix to calculate the enthalpy changes for the following. So this one's a little more complicated because we're not getting the enthalpy of formation reaction alone. We're going to use that to calculate the enthalpy change. So here, we're taking a look at 1 gram of phosphorus burns forming P4O10. So we're going to want to know P4O10 solid. We want to know what is the enthalpy of this reaction. So we have phosphorus and we have oxygen. Oxygen is going to have a 2 because it comes as a diatomic and it's a gas. Phosphorus is going to be solid. And here we're going to put a 4 here and we're going to put a 5 here to balance it. So looking in the back of the book in alphabetical order, I'm looking for phosphorus. So we have this P4O10. The formation reaction is minus 2984.0 kilojoules per mole. So the question is now, how much energy to take 1 gram of phosphorus forming P4O10? So I'm going to have 1 gram of phosphorus times 1 mole of phosphorus per, and I have to look up the molar mass of phosphorus, which is 30.97. And then what I'm going to do is I'm going to multiply by, according to this reaction, minus 2984.0 kilojoules per 4 moles of phosphorus. Okay, so that is going to be the energy expended when 1 gram of phosphorus burns. So the 4 comes from the balanced reaction here. Okay, so when we multiply this out, you can see basically I have 3,000 divided by 30, which comes out to be around, I want to say 300. So let's see what we get. We're going to get 4 zig figs because of this number. And we get 2984 divided by 30.97. And because that's a negative, we get negative 96.35 kilojoules total for our 1 gram of phosphorus. Okay, now let's do the same for 2 moles of NO, which decomposes to N2 and O2. So we want to here write out the enthalpy of formation reaction for NO. So let's write it out. NO gas. And what is it made out of? It's made out of nitrogen and oxygen. They're both Honkelbriefs. They're both gases at room temperature. And to balance this, I'm going to have to put a 1/2 here and a 1/2 here. And when I look up this reaction in the back of the book for NO gas, it's 90.29 kilojoules per mole of reaction. So here, I want to react, or I want to make 2.0 mole. And actually, I shouldn't say I want to make 2.0 mole. I want to decompose this. So here, this is going to be decomposing into this and this. So I've got to reverse this reaction. So this is the enthalpy of formation reaction. I can reverse the reaction. And here, I'm going to put enthalpy of reaction instead of enthalpy of formation, because this is no longer a formation reaction. Formation reaction is 1 mole of a substance, not 1/2 mole of 2 different substances. But however, I get this value from the one above, it's negative 90.29 kilojoules. So remember, Hess's law says that if we reverse a reaction, you also reverse the sign on the enthalpy. So that means that for my 0.2 moles of NO, we're looking at negative 90.29 kilojoules per 1 mole of NO. And so 0.2 times, I've got too many pieces of paper rolling around here. So 2 moles, or 0.2 times 90, is going to be about 1.8, right? Or 18, I should say. So let's see what we get. 90.29 times 0.2. And here we're going to get 2 zig figs. So we get 18 kilojoules of energy. And it's going to be negative. So that's actually energy released. So here's the answer for the second one. So for a problem like this, I would expect to see the enthalpy of formation reaction. I'd expect to see this being written in reverse and then this calculation. And for the above one, I'd expect to see the enthalpy of formation reaction. And then I'd expect to see the multiplication to get the final answer. Okay. Now let's take a look at another way to use enthalpies of formation. that would be as follows. You can get the enthalpy of a reaction by using the following formula. The enthalpy of the reaction is equal to the sum of the moles of a reactant, or a product, I should say, times the change of enthalpy of formation for that product, minus the sum of the moles of reactants. So here, we're going to see how this plays out. And I'm going to do this very methodically so that hopefully you can follow along and understand this better. Okay? So if you don't understand this right now too well, that's okay. Let's go over it a little bit more here. This means sum of, this is the moles of a particular product, and this is the heat of formation of a particular product. So we'll take a look here at a particular example. So nitroglycerin is a powerful explosive that forms 4 different gases when detonated. So here, nitroglycerin here we have as a liquid. When you detonate it, you get this gas, this gas, this gas, and this gas. And these gases are superheated. They don't tell you that this is an exothermic reaction, but it is. So when you heat these gases, they expand. And when you have all these gases being made and they're expanding quickly, that's a bomb, okay? So calculate the enthalpy change that occurs when 10 grams of nitroglycerin is detonated. The standard enthalpy of formation of nitroglycerin is minus 364 kilojoules per mole. So here we have nitroglycerin, which is C3H5NO3 liquid, and its standard enthalpy of formation is minus 364, and I'm going to put kilojoules per mole up here. So we need to find these values here for the rest of these. So what about N2? What is the standard enthalpy of formation for N2? Well, maybe it would help for us to write out the reaction a little bit. And what I'm going to do here is I'm going to go ahead and write this out on a separate piece of paper. So here we've got nitroglycerin C3H5NO3, and the standard enthalpy of formation in kilojoules per mole is given as minus 364. Now, what about N2? N2 gas. What is the standard enthalpy of formation for that? Well, let's write out the reaction. So we want to take N2 gas and we want to make it from its elements. So what are the elements in nitrogen? Well, nitrogen. Is nitrogen a Hunkelbrief? You bet. What is the standard form of nitrogen? It's a gas. So how much energy does it take to take 1 mole of gas and turn it into 1 mole of gas? The enthalpy of formation for this is exactly 0. So here we can write a big old 0 there. Now next we have O2. So for O2, which is a gas, what is the enthalpy of formation reaction? Well, it's O2 gas. So what is the enthalpy of formation for this guy? It is also a 0. Now, what about the CO2? Well, let's take a look. CO2 gas, we're going to look this up in the appendix. And so I'm going to go to carbon, and I see here a CO2 gas, and it's minus 393.509 kilojoules per mole. And lastly, we have H2O gas, and we've seen this in a number of examples today. It's minus 241.83 kilojoules. The appendix actually gives us more significant figures than the chapter did. So these are the values that we have for these different materials. So the enthalpy of reaction is going to be the sum of N times the enthalpy of formation of the products minus the sum of N times the enthalpy of formation of the reactants. So let's work with the products first. This is going to be one product. So it's going to be 2 times the enthalpy of formation of C3H5NO33 liquid. So I'm going to put a bracket around that for the products. And then minus, and I'm going to put a bracket here, and I need to deal with the reactants one by one. So here, I think it's easy to see that for this one, we don't need to worry about it because it's going to be, well, we'll go ahead and write it down. 3 times the enthalpy of formation for N2 gas, and then plus 1/2 times the enthalpy of formation of O2 gas, and then plus 6 times the enthalpy of formation of CO2 gas, and then plus 5 times the enthalpy of formation of H2O gas. And then I'm going to end my bracket there. So when I plug in the numbers here, oh, and I'm sorry, you can't see that. So let me move this up just a little bit so that you can see what I have done. I know my hand gets in the way, but you know, when I'm writing below the screen, that doesn't help one bit. So here I have 2 times the enthalpy of formation of, oops, and I did it exactly wrong, didn't I? This is supposed to be products. So this is supposed to be over here, and this is supposed to be over here. So I can correct this by putting a plus here and a minus here, and that fixes it, okay? So here, this all belongs here, and so I'm going to rewrite this as 3 times the enthalpy of formation of N2 gas plus 1/2 times the enthalpy of formation of O2 gas plus 6 times the enthalpy of formation of O2 gas plus 5 times the enthalpy of formation of H2O gas. So these are the products, and then minus 2 times the enthalpy of formation of my C3H5NO33 liquid. So this is the same as I've written above, only in a better order that reflects what the formula shows. So now I can go ahead and cover up the problem, reset, and now I have the formula that I'm using and I have the numbers right here. So let's go ahead and plug them in. So here I'm going to have 3 times the enthalpy of formation of nitrogen, which is 0. I'm not even going to put units there because 3 times 0 is 0. Plus 1/2 times 0 for oxygen, plus 6 times the enthalpy of formation. This is supposed to be CO2. And we have negative 393.509 kilojoules. And then plus 5 times negative 241.8 kilojoules. And my bracket, and then minus 2 times minus 364 kilojoules. So just to show all the work, I'm going to put 0 plus 0 minus, so 6 times 400 should be 2400 or negative 2400, close to that, right? So times 393.509, 6 significant figures, that's a lot. So I get minus 2361.06 kilojoules, the negative from there. Here I have negative 241 times 5, which should be close to negative 1200. So 5 times 241.8 is equal to negative 1209 kilojoules. 4 zig figs and 4 zig figs. Oh, I should have had a 3 there. So 241.83 times 5 is 1209.2. And I'm going to end my bracket, and I'm going to put minus 2 times 364 should be close to 700, negative 700, right? So 364 times 2, and I get 728 kilojoules. So let's clean it up just a little bit more. So this is going to be equal to, we'll add these two numbers together, 2361.06 plus, well, I'm going to put plus 1209.02, and we get negative 3570.08 kilojoules. Now this is really only good to the 0 because of that guy there is only good to the one place past the decimal. And then here I'm going to put plus, because we have the negative of a negative, 728 kilojoules. So we have this negative value here, negative 3570.08 plus 728. And we get negative 2842 kilojoules. And there's your answer. It's only good to the ones because this is only good to the ones. And that is the amount of energy for this reaction that we were just looking at. Let's see if I can find it. So that's the amount of energy for this reaction. So now we can write down, well, we don't want to write that down. This is the amount of energy change. And now we're supposed to calculate the standard or the change that occurs when 10 grams of nitroglycerin is used. All right, so let's calculate that now. So for this reaction, I'm going to write out 2C3H5NO33 liquid turning into 3N2 gas plus 1/2 O2 gas plus 6 CO2 gas plus 5 H2O gas. The enthalpy of reaction is minus 2842 kilojoules per mole of reaction. So we're going to combust 10 grams, as we say here, 10 grams of nitroglycerin. So I'm going to put nitro, instead of writing that out, times 1 mole of nitro per, well, let's look at the molar mass here. We have 3 carbons, which is 36.03 grams. We have 5 hydrogens, which is 5.05 grams. We have 3 nitrogens, and each nitrogen is 14.01. So 14 times 3 is 42. So 42.03 grams. And then we have 9 oxygens. Each oxygen is 16. 9 times 16 is 90 plus 54, which is 134, I think. I'm going to double check that one. So 9 times 16, it's 144. I didn't add right correctly in my head. So I'm going to add these numbers together, plus 42.03 plus 5.05 plus 3, or excuse me, 36.03. So we get 227.11 grams, and we would round to there because of this 144.0. So we're going to write 227.1 grams of nitro, and then times, according to this reaction, minus 2842 kilojoules per 2 mole of nitro. And this 2 comes from right there. Okay, so now let's write out or find out the answer. This should go into this about 10 times, a little bit more, maybe 12 times. And 12 divided by 2 is 6. 6 times 10 is 60. So the answer should be around 60 if I've done this in my head correctly. And we get 60, and here, because of the 3 significant figures, we get 62.6 kilojoules. And it's negative, and the negative means exothermic. So this is energy released in the reaction, and this is an enormous amount of energy. To give you an idea of what amount of energy this is negative 15 kilocalories. And remember, 1 calorie is a significant amount of energy. This is negative 15,000 calories for only 10 grams of material. And I can guarantee you that a stick of nitroglycerin, a stick of dynamite, which has nitroglycerin in it, has more than 10 grams of nitroglycerin in it. So this is a big boom. Okay, so that's how you use that formula for figuring out the enthalpy of the reaction. All right, let's try another one though, just to try to seal the deal. And here we go. Enthalpy of reaction from enthalpies of formation. The standard enthalpy of formation of solid barium oxide, BaO, is minus 553.5 kilojoules per mole, and the standard enthalpy of formation of barium peroxide, BaO2, is minus 634.3 kilojoules per mole. Calculate the enthalpy of reaction for this reaction where we take the peroxide and it decomposes to make the oxide and oxygen, and draw an energy level diagram. Okay, so to calculate the enthalpy for this reaction, I'm going to start with this. It's going to be the sum of N, the enthalpy of formation of the products, minus the enthalpy, N times the enthalpy of formation of the reactants. And one of the ways to remember that it's product and reactants is this is like a change type of thing, and change is always final minus initial. And in a reaction, the final are the products, the initial are the reactants. So more specifically, this is going to be looking at the products. I'm not going to make that mistake again. We have 2 moles of barium oxide plus, and I'm going to put brackets around this, 1 mole of oxygen. Okay, minus 2 times the enthalpy of formation of barium superoxide. Okay, so let's go ahead and look up these numbers. So we have that the barium oxide, the enthalpy of formation in kilojoules per mole is minus 553.5. Barium superoxide is minus 634.3 kilojoules. And O2, which is the other thing we need to look up. I'm going to look it up in the book here. And let's see, O2, alphabetical, lead, phosphorus, oxygen. So here it is. For O2 gases, oh, 0. Oh, I didn't have to look that up because the reaction to make O2 gas is to start with O2 gas. So of course it's 0. The enthalpy of formation of any element in its standard state is 0. So now we can plug the numbers in. We have 2 times the enthalpy of formation of barium oxide minus 553.5 kilojoules plus 1 times 0 minus 2 times negative 634.3 kilojoules. So I'm going to plug these numbers into my calculator, and we can see 2 times that is going to be minus 1100 approximately. And it's minus 1107 kilojoules, and then minus, and here I'm going to actually make that a plus because we have the negative of a negative here. So we have plus 1268.6 kilojoules. This is really only good to the 8 because 4 zig figs here, 4 zig figs here. And so when we add these two numbers together, we get 616 kilojoules is the enthalpy of the reaction. And there you go. Now, what is the other thing we're supposed to do for this? We're supposed to draw an energy level diagram for the decomposition of Ba barium superoxide to barium oxide and O2, and the enthalpies of formation of barium oxide and BaO2. So here, we want to write out the enthalpy of formation reactions for barium oxide and barium superoxide and combine it with this reaction here. So I'm going to get a fresh sheet of paper here, and I'm going to write out all of these reactions. So we have 2 BaO2 solid turns into 2 BaO solid plus O2 gas. And we just found out that this reaction is plus 1616 kilojoules. Now, the formation of barium oxide, the formation reaction is minus 553.5 kilojoules. And we're going to start with barium and oxygen. Oxygen is a Honkelbrief, and it's a gas. Barium is not a Honkelbrief, and it's a solid. How do I know it's a solid? Well, because it's a metal. Okay, to balance it, 1 barium, 1 oxygen, 2. I need half here, so I end up having 1 oxygen. Now, for barium superoxide, and this is a solid, and this is also a solid, we're going to start off with barium and oxygen. This is a 2, and it's a gas, and this is a solid. And here it's already balanced. And the enthalpy of formation for this is minus 634.3 kilojoules per mole. So I have all 3 reactions written out, and I have these written out, and we're supposed to draw an energy level diagram that shows the relationship between this, and this, and also O2, okay? Well, actually, I should say this decomposing to this and these two. So I have everything I need right here. Now, I want you to recall that when I draw these out, I like to start with the one that has the biggest number in front. So I don't worry about the sign. I just look at the size of the number. 16,016 is much bigger than 553 or 634. Now, since that's a positive value, I'm going to draw an arrow going up. How far? 1,616 kilojoules. And then I'm going to draw a line across. And what do you always put at the head of the arrow? You always put the products. So the products are 2 barium oxide solid plus O2 gas. And once you put that at the head of the arrow, what do you always put at the tail of the arrow? The reactant. So barium superoxide solid. So I've written the first reaction in, and now I'm going to add these two in. So which one am I going to add in? Well, it depends. Do I want to start at the top or start at the bottom? If I start at the top, I want to find which one of these reactions has barium oxide or O2 in it. Well, they both have O2 in it, so I probably want to stay away from using O2 to decide. But here I have barium oxide, and here this reaction has barium oxide. This one does not. So I'm going to put this one in here. Now, we need to think about this a little bit. You can see I'm going to put this reaction in here, and it's going to have a negative value. So that's going to be an arrow up or an arrow down. And the answer is an arrow down. How far? Negative 553.5 kilojoules. Now, did you see me take my ruler out to make sure that this is proportional to this value here? And the answer is no, you didn't. Because I don't need to. Oh, and I think I have the wrong number here. Now that I think about it, we got to back it all up. So here, I didn't do this correctly. See, this is what happens when you don't use your mind and estimate. So I'm going to clear this, turn it on, and I'm going to put negative 1107. Clear. It's 161.6 kilojoules. Darn it. So I got to go back here and I got to call this 161.6 kilojoules. So that's the answer. And now I need to take my energy level diagram and I'm just going to cross it out because I don't want to erase all of that mess. So now I'm going to start over. Now, which of these is the largest? Looks like this one is, right? So I'm going to draw an arrow down. How big? Minus 634.3 kilojoules. And I'm going to put this value down first. Let's see. I'll put the products at the head. So this is barium oxide, solid. And then I put barium and oxygen here. And then I want to incorporate either this or this into the reaction. I'm going to go ahead and work on incorporating this. And you can see here I have barium oxide and I have an arrow going down and that's a product. So I'm going to draw another arrow, but this one's going to be 553.5 kilojoules. Okay. Now, you can see I'm going to have to do a little bit of manipulating here, but I'll show you what I'm going to do in just a minute. Here, you can see that, oh, you know what? I just need to start this one over again. So I'm going to go back to right here, because all of this is good up till now. And I'm going to rewrite these reactions a little bit. And we're supposed to show the relationship between the enthalpy change for the decomposition of barium oxide to barium oxide and O2 and the enthalpies of formation of barium oxide and barium hydroxide or superoxide. So let's start fresh. And I'm going to write the reactions out. And so we have 2 barium superoxide solid turning into 2 barium oxide solid plus O2 gas. And the enthalpy of formation is equal to 161.6 kilojoules, not 16,006. We also have that barium solid plus 1/2 O2 gas is going to turn into barium oxide solid, and the enthalpy of formation here is equal to negative 553.5 kilojoules. And then we also have barium solid plus O2 gas makes you barium superoxide, and the enthalpy of formation here is minus 634.3 kilojoules. Now, these 3 reactions should add up, if you will, to Hess's law. So I should be able to take this guy and make this guy. So I'm going to do a Hess's law treatment of this very quickly. So that I'm going to take this and make that. Okay. So here, if you take a look at this reaction, do you see the barium superoxide? And you see the barium superoxide here? So I want to use this reaction to make that, but I need to reverse it. And I'm going to double it. Now, why am I doubling it? Because I need 2 barium oxides. So here, the enthalpy of this reaction becomes this number made positive and then doubled. So 634.3 times 2 is 1,269 kilojoules. And then I want to take this reaction, and because I want this to be a product like this is, I'm going to write this reaction as is, but you see I need 2 of these. So I'm going to take this reaction and double it. So I get barium solid plus, I'm going to double it. So I'm going to put 2 bariums plus 1 oxygen. Gives you 2 barium oxide. And for that reaction, since it's no longer an enthalpy of formation reaction because I've doubled it, we're going to double that number. And these numbers should look familiar to us because we saw them before when we did the sum reactions. So here, when we add these 2 together, we can see that one of these O2s cancels with one of those, and we're left with 1 O2. You can see that the 2 bariums cancel with the 2 bariums, and we end up getting 2 barium superoxide turn into 2 barium oxide plus O2, and we add these 2 numbers up, and we get that the enthalpy of this reaction is the 161.6 kilojoules. So this is that number there. So I want to write the energy level diagram for these 3 things. So I'm going to start with the biggest number. And since it's a positive number, it's going to go up like that. On the head of the arrow, I put the products. So the products are 2 barium plus 2 O2. And on the tail of the arrow goes the reactants. Okay, now I'm going to try and incorporate the next one. So it's either going to be this one or this one. And here, since this has barium in it and this has barium in it, I'm going to incorporate this one. And since this is a negative 1100, it's going to be an arrow down that goes down negative 1107 kilojoules. And that reminds me, I need to put positive 1269 kilojoules here. And here we're going to be reacting 2 barium plus 1 oxygen. So here, remember there's 2 oxygens here and we're only using 1 of them. We're going to make 2 barium oxides. Now, this isn't good enough for me because if you take a look going from here to here, we have 2 bariums, 2 bariums, 2 oxygens, 4 oxygens. It doesn't work. So there happens to be extra oxygen, and now it works out. 2 bariums, 2 bariums, 2 oxygens here, 2 there for 4. 2 times 4, we got 4. So that's a little tricky. And now I'm going to put this one in, and clearly since it's positive, it's going to be an arrow up, 161.6 kilojoules. And here we're supposed to have the products at the end of the arrow. And here we have it, 2 barium oxide plus O2. And we're supposed to start with the superoxide and we're done. So there's your energy level diagram. So here, this has higher potential energy and it's less stable. Here, this has lower potential energy and it's more stable. So when you tend to make this barium superoxide, it tends to be more stable than barium oxide or barium or any of these other things. And that's your energy level diagram. So a little bit tricky, but do you see how that if I went to Hess's law and made everything match up and add together, then it was a lot easier to put this into an energy level diagram. So you want to keep that in mind when you're drawing your energy level diagrams on your exam. Okay, well, that's it. And that's the end of this particular module. There is one more section in the book that we're not really going to cover. It's not that essential. All right, thank you for listening.